Hello. Today we are going to talk about inscribed angles and polygons and angles and secants formed by chords, tangents, and secants. So, the first bit of vocabulary we're going to start with today is what is an inscribed angle? An inscribed angle is an angle whose vertex is on the circle, so it's on the outside, and whose side contains the chords of the circle. So here, the sides of the angle are AD and DC. If you recall up until now, our angle has been the central angle, which the central angle is drawn out of the center of the circle. An inscribed angle is an angle whose is formed by it's a point on the outside of my circle is my angle. And then, of course, I have the two chords making up the angle. An intercepted arc is basically the arc that is formed by the inscribed circle. It's an arc that lies on the interior of the inscribed angle and has endpoints on the angle. It's basically the arc that's formed by the inscribed angle. That's what it is. It's the arc that's formed by the inscribed angle. Inscribed polygon is just a polygon in which all of its endpoints or vertices lie on the circle. So it's just a polygon trapped inside of a circle, but its endpoints are on our circle. And we can't have a point in the middle of any in space. Circumscribed circle is just a circle that contains the vertices of the inscribed polygon. So basically, he right here is my circumscribed circle. He right here is my inscribed polygon because he's inscribed inside the circumscribed circle, basically. So with that, we have a few theorems. New vocabulary always promotes new theorems. So first, to measure an inscribed angle, it's not like it was before. If you recall in our last notes, we had a circle, we had an angle out of the center of the circle, and whatever the angle was, that was also the measure of my arc. They were the same because he was in the center, it's the same. But when I have an inscribed angle, it's not the same measure. He's pushed back. So basically, this arc measure here is twice the angle. So whatever my angle is here, my arc is 2 times it. If you think about it, he was the same when he was right here, but now that he's pushed back, the angle's gotten skinnier on the other side, so he's smaller. Okay? So it says the measure of angle ABD going the other direction is 1/2 of the measure of this arc. So if you think about it, he's really large here, pushed back. If he was right here, he'd be the same thing. He'd be at a big angle. It's just all where the vertex is sitting of the angle. So when I have an inscribed angle, he's twice the arc. Central angle, he equals the arc. Theorem 10.8. If 2 inscribed angles of a circle intercept the same arc, then the angles are congruent. What it's saying here is, I have this angle that goes like this. Here's his arc. I have this angle here that goes like this. Here's his arc. They open up to the same arc. They have to have the same measure. And because they're inscribed, as we just learned, it's going to be half whatever that arc measurement is. So the measure of angle ABD is congruent to the angle ACB. They open up to the same arc, they have to have the same measure. There's no discrepancy in them. And you know that, again, their angle measure is half the arc. Theorem 10.9. In a right triangle, a right triangle is inscribed inside of a circle. Then the hypotenuse is the diameter of the circle. Conversely, if one side of an inscribed triangle is the diameter of the circle, then the triangle is a right triangle and the angle opposite the diameter is the right angle. All right, basically, let's just think for a second. If my diameter is through the center, then the degrees across it are going to have to be 180 because it's a semicircle. So then we know that if we look at the arc from A to C, if it's 180 degrees of the opening, we know that the inscribed angle is half of it, so he has to be 90. So it makes sense when you're talking about it that if he's a semicircle at 180 degrees, then the angle formed that's inscribed has to be half of it, or 90 degrees, which then creates our right triangle. Okay, Theorem 10.10 says, a quadrilateral can be inscribed inside of a circle if and only if its opposite angles are supplementary. Now, this is different from what we learned last unit. Last unit, we did not have the quadrilateral trapped inside of a circle. Because he's trapped inside of the circle, that means that he only has 360 degrees to totally play with. If you think about it, if I have just the distance here from E to G, then the distance on this other side of EDG has to be 360 minus it. So any way you look at it, completely the two together are going to be half of 360 degrees, because together they're going to make 360. So therefore, it has to be 180 degrees, so therefore it has to be supplementary. So opposite angles, so like D and F is opposite, are supplementary. E and G are supplementary. Theorem 10.11. If a tangent and a chord intersect at a point on the circle, then the measure of each angle formed is half the measure of the intercepted arc. You're going to notice in here the theme is a half. So it's saying that here I have angle 1. Angle 1, its measure for right here is half of the arc created between A and B. So the measure of angle 1 is half the measure of arc AB. The measure of angle 2 on the other side is going to be half of the measure of BCA. Half is the theme. And think about it. Whenever I have an angle inside, he's half of it. He's half the arc, he's half the arc, and the front, he's half the arc. All right, our last two theorems. The first one has to deal with two chords intersecting inside of a circle. So here I just have Mr. Chord CB and DB and chord AC, and they cross in the center of the circle. So what the theorem tells us here, it says if two chords intersect inside of a circle, then the measure of each angle is 1/2 the measures of the arc intercepted by the circle and its vertical angle, which means if I'm looking here at angle 1 is going to be 1/2 of CD plus BAB. If I'm looking here at angle 2 is 1/2 of AD plus BC. So it's saying that if I want to find the measure of angle 1, it's 1/2 the measure of this arc plus this arc. He's like an average of the two. If I'm looking for the measure of angle 2, he's 1/2 the measure of AD and CB. Because he crosses inside, we're going to add the 2 and divide by 2, or add the 2 and take 1/2. For Theorem 10.13, it's saying, okay, I'm looking for an angle on the outside. It doesn't matter whether he's a secant and a tangent and a tangent, or two secants. That doesn't matter. they're talking about to find that external angle, you're going to basically then take 1/2, because everything's a half, of the larger minus the smaller. To find angle 2, larger minus the smaller. Angle 3, larger minus the smaller. So every time you're trying to find that external angle, it's always going to be the outside minus the inside. The outside minus the inside, 1/2 of it. 1/2 of it. It doesn't matter which situation occurs at all. All right, so let's play around with all this mess. Number one, you got to kind of think of what's going on. Okay, so number one, you got to kind of think about what's going on. So, on number one, it says, I want to find the measure of angle S. Straight form, theorem 10.7. It tells us, I'm trying to find this angle here. He is 1/2 of 60. So, the measure of angle S is 1/2 of 60. So, the measure of angle S is 30 degrees. It's an angle measure. You're going to have a degree. Now, B is the one that gets a little tricky. It says, hey, I want to find RQ over here. So how am I going to do it? Well, two things are going on. One, I know that I have an inscribed angle that's 37 degrees. So to work it out, it's 2 times that 37 degrees, or 74 degrees. So I know that QS is 74 degrees. I also know that here is a semicircle. How do I know that? Because RS is a chord through the diameter, which means he is a chord through the center, so he's a diameter. So that total degrees of that blue is 180 degrees because he's a semicircle. But I know that 74 are taken up here, so to find the difference, I just subtract the 74 that I am given to find the missing piece of 106 degrees, which then is the measure of RQ. So just to recap, this is where it gets a little tricky with this stuff. Is one, I have a diameter. That means I have a semicircle, so 180 degrees from R to S. Q to S is 74 degrees, so 180 minus 74 is RQ. Okay, on number 2, it says find the measure of HJ and the measure of angle HGJ, and what do you notice? All right, so first, here's my angle, here's my arc. Going outward, he's 2 times the 39, so he is 78 degrees based upon theorem 10.7. Inscribed angle working its way out. Now we're looking here at the second angle that comes across like this. He opens to the same arc, so therefore he must have the same measure. So therefore, theorem 10.8 tells us that the measure of angle HGJ has to equal the measure of angle HFJ, which then is the 39 degrees. All right, number 3. Number 3 says, name 2 pairs of congruent angles in this figure. Well, the 2 that open up to this arc come this way and this way. That means they're congruent angles. So, angle, oops, that's an angle symbol. P, no, it's not P, sorry, it's SPR is congruent to angle SQR. Then, if we open up to this arc on this side, I have this angle here and this angle here. So that's my second pair of angles. Angle QSP is congruent to angle PRQ. It's just when they open up to the same arc, the two angles are congruent. Again, theorem 10.8. Okay, on number 4. Number 4 says, a security camera rotates 90 degrees and needs to be able to view the width of the wall. The camera is placed in a spot where the only thing that can be viewed when rotating is the wall. But you want to change its position. So where else can I place it? If you think back to theorem 10.9, it tells us that as long as the wall or the side is the right angle of a right triangle, or it's not a right angle, is the hypotenuse of a right triangle, then the whole side can be viewed. So if we look at the possibility of having a circle, then anywhere on this circle that I can make a right triangle, I can make a right triangle coming this way, that's the right angle, he can be a security camera. If I can make a right triangle coming this way, he can be a security camera. If I can make a right triangle coming this way, he can be a security camera. If I make a right triangle coming this way, he can be a security camera, and so forth, and so forth. It's wherever I can make that right triangle, the security camera can be placed, because as long as the hypotenuse is that wall, I'm good. Okay, number 5, find me some variable. All right, so I have a quadrilateral inscribed inside of my circle. So how am I going to find my variable x and y? Very easily. Theorem 10.10. Theorem 10.10 states that the opposite angles, a quadrilateral is inscribed inside of a circle, then the opposite angles are supplementary. So here, Q and S are supplementary. So 88 plus x is supplementary. Here, P and R are supplementary. Done. Does it matter when I have a different quadrilateral? No. Perfect. Okay, on number 6. We want to find the measure of angle 1. To find the measure of angle 1, we need to apply the next theorem we know, 10.11. With theorem 10.11, it says, all right, if I want to find the measure of angle 1, it is the result of 1/2 of the arc AB. The arc AB is 132 degrees. It's on the outside. So the measure of angle 1 is 1/2 of 132. It's a measure of an angle. It has a degree. On B, we want to find the measure of the arc, EFD. So now, just going backwards, the measure of that angle is going to equal 1/2 the measure of that arc. Multiply both sides by 2. Perfect. All right, on number 7. Number 7, I have two chords crossing inside of a circle. If you recall on Theorem 1012, it says if two chords cross inside the circle, then to find the angle that's vertical associated with the arcs, that you just take 1/2 of the two arcs added together. So that was Theorem, I think, 1012, if I'm correct. So I'm looking for x. His vertical association is arc FJ and arc GH. So x equals 1/2 the measure of arc FJ plus the measure of arc GH. B is a little bit different. X is external. It is outside of my circle with a secant and a tangent. So when x is outside, we have JF minus HF. So when the angle is outside, you're going to subtract the two corresponding arcs. When the angle is inside, you're going to take 1/2 of adding the two related arcs. Number 8 just says, I'm flying an airplane about 5 miles above the ground. What is the measure of arc BD? In the part of the Earth that you can see it. The Earth's radius is 4,000. So if the Earth's radius is 4,000, then CD is 4,005 because he's 5 miles above the Earth. So it says here, how am I going to find this mess? Well, first of all, we know that B and D are tangent to the circle. Or sorry, actually, CB and CD are tangent to the circle. So therefore, we know a couple things. One, we know that this angle and this angle are going to be congruent, or this side and this side are going to be congruent. We also know, though, that this is a 90-degree angle. So angle D is a 90-degree angle and angle B is a 90-degree angle. With that, we do know that the two triangles are congruent. Why? Because here I have the right angle is the side is 4,000, the side is 4,000. I'm just going to make these two congruent because I don't really know that they are. I also know that this piece is congruent to itself. So I know that these two triangles are congruent by side, side, side. So I know that CB and CD are tangents. I know that angle B and angle D are right angles as a result. And I also know that triangle ABC is congruent to triangle ADC by side, side, side. I need to find the measure of this angle here at the bottom. So the measure of angle BAD is my question mark. So if I just look at half of this, I have a right angle. I have a hypotenuse. And I have an adjacent angle to the angle that I'm trying to find, CDA, that I can double. So with that, well, one, I have a right triangle. Who shows up to the party? The Pythagoras, but I'm not looking for a side, or SOHCAHTOA. Here it happens to be SOHCAHTOA, which means that I know the cosine of this angle DAC is going to equal the adjacent over the hypotenuse. So the cosine -1, so the measure of angle DAC is going to be my inverse cosine. Which, first, I need to change my calculator to degrees. Second, I need to go ahead and put it in. And I get 2.86 degrees, because that's what the measure of the angle is. But I know that, again, these two angles are congruent angles. I only found this little angle here, so now I can double it or multiply it by 2 to get the measure of angle BAD, BAD. So my measure of that angle is about 5.8 degrees when I multiply it by 2. Long-worded application problem, probably used a lot in real life to find the angle something is off the ground or a roundabout. Just take what you know. When I see tangent, I know 90 degrees. When I see 90 degrees, I know Pythagoras or SOHCAHTOA, depending on what I'm trying to find. Because I'm trying to find an angle, I can't use the Pythagoras. I have to use SOHCAHTOA. Last but not least, on number 9, I'm putting 3 stars because this actually is not included in, we're not going to do it in the homework tonight. We're actually going to use this in the homework after the quiz because it's a nice little lesson. We can do a couple problems to practice. It's important, and I'm going to go through it now instead of next class, but it's important because whenever I'm trying to find a length, on this one right here it says, given this circle, AB is 7, so this whole distance is 7. The measure of ACO, O is my center, sorry, is 22 degrees. AB is the diameter, which means that he's a radius at 3.5 and he's a radius at 3.5. And so I'm going to find the length of the arc. Up until now, we have found the measure of the arc, not its length, how long it is. To do this, we have to set up a proportion to what we know. It's a formula, not on the formula sheet. It's one you need to know, and that's why there's going to be a proportion. We know that arc measure, that's its measurement, to, well, how many total degrees are in my circle? Correct, 360. So the part that we're looking at, that's the arc, to the total degrees, equals the part that we're looking for in length to the total length around a circle. What's the total length around the circle? Correct, it's circumference. So our formula for circumference is 2 pi r. So it's saying the measurement piece, or the part, to the whole measurement, the arc length part to the whole length. It's part to whole, part to whole. It makes a nice proportion. And really, whenever you're trying to figure things out, if you don't know what to do, proportions are wonderful. So now, using this information, I'm going to find AC. If I want to find the length of AC right here, he's my x. So what do we know? Well, what's the arc measure? It's on the central angle, so it's the same as the angle. Total degrees in my circle. I'm looking for its length, the radius. Now all I'm going to do is cross multiply and divide. So 360x equals 22 times 2 pi times 3.5. So I'm going to multiply that, divide by 360, and when I round, I get about 1.34. That is the length or the measurement from A to C. That's how long it is around my circle. Now it wants me to find CAD. Well, to find CAD, now I'm looking at this whole distance. I'm going to call the whole distance y, just use a different variable, doesn't really matter. That I still need the same formula. So, what is my arc measure? Well, he's 22 degrees, so using my arc addition postulate, he's 90, because of course they make a straight line, so he's 90. So 90 and 22 is what? Perfect. So the whole measurement of arc, CAD, over the total measurement in my circle. I want to find its length over, again, circumference of a circle, 2 pi r. Again, cross multiply. There's your final answer. Again, this is not in the homework tonight, but after the quiz on the next class, after the quiz, we will use this information. You have one of these on the test, not the quiz, because we're going to practice it after the quiz for homework, and then we will apply it later in the unit. It's the only true formula. It's also on the sheet of the stuff in the beginning, because while we're talking about arc measures, we all need to also talk about the lengths of our arcs as well. Well, thank you for hanging with me today, and I hope you have a fabulous evening.